So welcome to this video, which is going to serve as an overview of an example implementation of the strategy design pattern. So the first thing we're going to take a look at is an example of our strategy base class. Now, for this example, we're going to create a runner. Now, a runner as in someone that runs around. But let's say, for instance, it's the future. You have the ability to run naturally, or you have the ability to augment yourself. In other words, you can change how you run. Now, specifically, the thing that we want to change or swap out are our legs. So the basic thing that any runner has that is going to be interchangeable in the future are its legs. So the legs in this case serve the purpose of being our strategy base class. Now, as you can see, it's been declared abstract, which means we can't actually create any concrete implementations of legs. It also has an abstract method called run, and it simply returns a string. Now, because it's declared abstract, it means that our derived legs classes need to provide an override for this run method. So let's say we want to have different types of legs. Okay, so different ways to run. So the first thing we can do is, let's say we want to have robotic legs. Okay, so someone can have robotic legs in the future. Seems this is really just an augmented race, and you'll see the robotic legs inherits from the base class legs, and it overrides our run method and simply says, listen, I'm running on robotic legs. Then we also have a method in the future in which you can hover. So hovering basically says you are hovering on a flame booster. So in other words, you have a way of augmenting yourself to be a flame booster. And then we also have the ability to add tracks to ourselves. So the third type of legs that you can have is basically you're rolling around on wheeled tracks. Now, probably all of this could also work if we're saying this is a race between robots. So basically, you can have a robot that can run on robotic legs, a robot that can hover, or a robot that can roll around on tracks. So these are all versions, all three of these things have been versions of concrete strategies, since they all derive from class legs. Now, the last piece of our puzzle is the actual client. Now, the client is the runner. Now, whether this runner is an augmented human or whether it's a robot, doesn't matter. It's still going to be a runner. But the main thing is our client class, which is runner in this case, needs to have a behavior or an algorithm that is hot swappable. In other words, it can change during runtime. So you'll see over here we have a public legs variable called runner legs. Now, the better way to do this in C# would technically be to have a private variable and public get and set properties. But we're not focusing on that at the moment. We simply want to demonstrate the pattern. So making it public is just an easy shortcut way to show that you should be able to exchange this leg behavior or leg algorithm whenever we choose to. Now, we also have a constructor that receives a set of legs, in other words, a running behavior. And all that does is it assigns it to our legs variable. And then lastly, our runner has a run method. Now all that run method is going to do, it is going to call run on whichever type of legs are currently associated with the runner. Now this is pretty cool because legs is an abstract base class, and because all of our derived classes, meaning tracks, hover and robo, all derive from legs, it means by using the principles inherent to inheritance and polymorphism, we can actually treat objects of the derived classes as objects of the base class because they share the same method. It doesn't matter whether we call runner legs on that legs object. We could have tracks in there, we can have hover in there, we can have robo legs in there. It wouldn't matter. They all have a run method. So this is pretty cool. It means we don't need to know what is stored in there in order to be able to call run. Now something else that I've done, which isn't necessary for the pattern, but it's also cool to see that we can have different kinds of clients. So in this case, we have another kind of client that inherits from runner, and let's call this a tracked runner. So this is basically just a runner that is created to always automatically be associated with the tracks legs behavior or tracks legs algorithm. So basically it has a constructor, and the constructor simply initializes the base class runner with a set of tracks. So right, let's go to our main program and see how we set all of this up. So we have a first runner that we associate with robotic legs, another one with tracks, another one with the hover mechanism, the flame booster, and then we also create a tracked runner. So let's go and modify this just slightly so that we can see that behavior can change as well. So we'll say console.writeLine changing behavior, and then we'll say first dot runner legs equals, let's say it starts off being robo, so let's just say new tracks, and then we say first dot run again. Okay, so in this example we've created 3 runners and a tracked runner, and then we test what their outputs are. So in theory, when we say run for the first one, it should output what the robo does, second for tracks, third for hover, and this tracked runner should output the same as for tracks. Then we go and demonstrate that we can change a behavior at runtime by associating runner legs, over here the first one, which is robo, we associate tracks with that as well. So this first one that used to be robo will at runtime change to make use of tracks. Okay, great. So that's enough talking about it. Let's run it and see what it does. Okay, great stuff. So let's see what we get. So the first one says running on robotic legs. Second one says running on wheeled tracks. Third says hovering on a flame booster. Then the tracked runner, which is initialized with a set of tracks, says running on wheeled tracks. Then we change the behavior of first by assigning tracks to it as well. We execute its run again, and now it says running on wheeled tracks. Yeah, I think this is pretty awesome, since this allowed us to actually change how an object behaves at runtime without having to stop the program and then slot in a new behavior. Think if this was a game, if you could dynamically, while the game is running, change the behavior of a character in your game. Fantastic stuff. Now that's the end of this overview of an example implementation of the strategy design pattern. Play around with it a little bit, write your own versions, and above all, have fun. See you on the next video.